Saxon Algebra 2, Lesson 30. Do not let this scare you. Geometry proofs. Before I go any further, let me just say this. We're not going to really do geometry proofs in Algebra 2. I'm saving those for advanced mathematics. You can ask Laura and Vivian and Jayla how much fun they're having, because actually they are kind of fun. Working proofs, we're not going to do them in this class. Proofs are kind of like an ancient art, like whittling, hunting mastodons, and cross-stitching samplers, in that it's really nice to know about proofs and it makes you a very well-educated person. And they're interesting and fun, but in terms of your studies as a future university student in the year 2020, this is not necessary information for you. This is more fun to know than need to know. So what we're going to do in this lesson is just give you a little history of how this works and how geometry proofs came to be. And then we're going to just get to the practical part of it, the part you actually need to know. So let's go back through the ages of time. The very first mathematics in the Western world came from the Egyptians and the Babylonians, all right? We're talking way back in the Holy Land, right? And they were hacks, basically. The first ones who really figured it out were the ancient Greeks. And let's just write a few things down so we don't get bored. The ancient Greeks were the ones who really figured out a lot of stuff between 600 BC to 300 BC, okay? That's when they really got things humming. They figured out philosophy, they figured out pure science, they figured like chemistry and physics, they figured out applied sciences, which is like engineering things. They had political thought. They were historians finding things before them. They were killing it in all subject areas is what I'm trying to say. Pythagoras, Pythagorean theorem dude. He was one of these ancient Greeks. He was on an island called Samos, and then he was in southern Italy in this time frame. And there are some other ones. I'm not going to bore you with all their names, but the one we want to talk about today is a guy that we now call Euclid. He used to be called Euclides, and he was in Egypt during, if you're into Greek kings of Egypt, he was Ptolemy I. And he was really interested in geometry. So he's the guy that we're kind of following in this story. What he did was he came up with 10 postulates. And a postulate is a fancy name for a self-evident truth. And I'm going to show them to you in just a minute, and you'll be like, yeah, that's kind of a self-evident truth. And what he did was he defined these 10 postulates, which again, I'm going to show you in a minute. They're super easy. And he said, everything that is more complicated in geometry can be proved using these 10 postulates. I can take these 10 little tidbits and build with them to prove anything about geometry that you want to know. Which was kind of a cool idea because he wanted it all to be super grounded in reason. And he used something called deductive reasoning. Now, before I get into the postulates, I want to tell you a little bit more about deductive reasoning. And that's where the homework problems are going to come from. They're words, they're not numbers, they're kind of fun. All right, so deductive reasoning is a process, and it's easier if I give you an example, and then I'll give you all the fancy words. All poets are poor. This is something that we call the major conclusion. It says something broad about a group, all right? The next thing that I'm going to say, this is one. Roger is a poet. This is what we call the minor conclusion. And then we draw, oh, I'm sorry. This is premise. And this is premise. I'm sorry. This is the conclusion. If all poets are poor and Roger is a poet, then we can conclude that Roger must be poor. And the way that we can think about this is to say, here in our major premise, we identified a group. We didn't talk about poor people, we talked about poets. And then we said that Roger is a part of this group. So whatever we conclude about the whole group, we can now conclude about Roger. That makes sense, doesn't it? So we call this a valid conclusion. Now, we can sit here and argue, actually, poets are paid pretty well compared to other works. That's not the point. We're not using any other information from outside our two premises. We're simply going on this, and based on the information that we have, this is a valid conclusion. It may or may not be true, but it is a valid conclusion. Now let me show you a slightly different set of premises. And show you one that's false. This is called also syllogistic reasoning. Yikes, that's a mouthful. I don't even want to write it down. It'll just confuse you. Okay, so let's try another one. 1, all poets are poor. That's our major premise again. 2, Roger is poor. That's our minor premise. And now we have to conclude, is this, so 3, Roger is a poet. We're asking ourselves, is this a valid conclusion or is it not a valid conclusion? Again, our major premise is talking about the group of poets and describing them that are poor. It doesn't say only poets are poor. It says all poets are poor. Roger is poor. That doesn't mean he's a poet, does it? It could mean that he is on eBay late at night too much, but he might not be a poet at all. So this is not a valid conclusion. Okay, this is a little bit vague. Students either get this or they don't. If you don't get it, just think about the group that's being described and whether the minor premise is telling you something about that group or is telling you something about their quality. Because if our second thing just talks about the quality, it's not the same. If our second premise tells us about the group, then we are. All right, and here's a fun one. I'm just going to show you in the book. This first one is about geometry. It's not as interesting. This is my favorite. Major premise. All chickens have 3 legs. I mean, that's insane, but okay, let's say. Minor premise. Henry is a chicken. All right, then Henry has 3 legs. That is valid. Again, not necessarily true, but it is valid reasoning. Major premise. If it rains, I will go to town. Okay, so the group, so to speak, the condition is raininess. Minor premise, it did not rain. Conclusion, I did not go to town. And as we see, that is invalid because our major premise just tells us what will happen if it rains. It says nothing about what will happen if it doesn't rain. So we cannot draw a conclusion there. All right, and then let's do the first one. That's geometry. Major premise. all squares are rectangles. Okay, we know that's true, but we can wrap our heads around that. Minor premise, quadrilateral ABCD is a square. So squares is the group, rectangles is their property, their condition. This one is part of that group. So yes, we can say that quadrilateral ABCD is a rectangle, right? This was like Roger being a poet. Okay, so for your homework, the main thing John is going to ask you to do, and I'd like you to do both of them, is look at these. There's a major premise and a minor premise, and then you have to decide if the conclusion is valid or not. All right? If these are blowing your mind, tell me in the video, tell me when we chat, and I'll try to talk you through it. All right? Now, what Euclid did is he said, I'm going to take my postulates and I'm going to use this deductive reasoning to build logical arguments to explain why certain things in geometry are true. So that was very cool of him. Let's take a look at his 10 postulates. They are also in the book. They're not anything you need to memorize or remember per se, but they're really great for you to know. And then next year, we're going to play around with them a little bit. Postulate number 1, 2 points determine a unique straight line. Well, yeah, for any 2 points that you draw, there's only one line that connects them. A straight line extends indefinitely far in either direction. We've been saying that since like Geometry 101, haven't we? A circle may be drawn with any given center and any given radius. So what he's saying is, if I make a dot for the center of my circle and then I pick a certain length radius, let's say that, I can draw a circle. Pretend it's perfect. Oh my gosh. Your imaginations have to go really wild. That's what that one's about. Yeah, that makes sense. All right angles are equal. Yes. Given a line N and a point P, not on that line, there exists in the plane of P and N, so in other words, not 3-dimensional, just 2-dimensional, there's only one line, which we're calling M, that passes through P and is parallel to N. All right, let me just draw that one too. That one's kind of confusing. Here's a line. Here's a point that's not on the line. There's only one line that we can draw that goes through the point and is also parallel to that line. All right, I believe that. Things equal to the same thing are equal to each other. Heck yes. If equals are added to equals, the sums are equal. Yes. If equals are subtracted from equals, the remainders are equals. These are the rules of algebra we use all the time. Figures that can be made to coincide are equal or congruent. That has to do with spinning and flipping things, right? We can move figures around mentally to make them line up. And the whole is greater than any part. I don't even know what that means, but sure, I can agree with that. So this is what Euclid did. He defined these 10 postulates, these 10 truths, and then he uses those to prove things. Now, I'm not going to get into detail on this because I don't want to go down the road of proofs right now. It's not necessary or helpful for you, but I just want to show you one of them so that you get the idea of how proofs work. Okay, we have often said that vertical angles are equal, right? I'm going to call this one X, this one P, this one Y, and this one Z. I don't like the way those letters are arranged, but I'm going to make it like John did. Okay, so we've said that vertical angles are equal, and let's just say specifically, we want to prove that Y and Z are equal to each other. They're congruent. Okay, so what we have to do when we're building a proof is we have to start logically building a plan as to how we're going to show this. And that's the hard part of proofs, is figuring out, how am I going to show this? It's easier to follow somebody else's thinking. So walk with me on this. We can see that this is a straight line and that x plus y have to equal 180. That's not even important, right? But we know x plus y equals 180. And then we can do the same thing with this line, right? And we can say x plus z also equals 180. Right? Because if this is the straight line, then these guys have to equal 180. And when this is the straight line, these guys have to equal 180, right? So we can say that these things are true. And then what we can do is we can use his postulate saying if two things are equal, then they're equal to each other. If these both equal 180, then we can say x plus y equals x plus z. Makes sense? If they both equal 180, we can say they're equal to each other. And then we can subtract x from both sides and say y equals z. And that's exactly what we set out to prove, isn't it? That y was equal to z. So that's how we can use these postulates. And I didn't really identify exactly. Let me just help you with that. The sixth one, things that are equal to the same thing are equal to each other. That's the sixth postulate. That's what I used right here. These two are both equal to 180, so they must be equal to each other. And I wrote that here. And then it's the eighth postulate that allowed me to subtract, because the eighth postulate says if equals be subtracted from equals, the remainders are equal. So we subtracted equals from equals, and we got this. So that's how the postulates are used to prove that some of these rules about geometry that I've just been telling you, hey, it's true, vertical angles are always equal. Euclid's postulates allow us to prove it by following these interesting little storylines that find a way to break it down so that we can see that it really does work out the way we thought. This is what a proof is like, you guys. It's got a very specific format, but that's the idea, is that we take a rule that we've been told and we can prove it. Thus the name, proofs. There are none of these in the homework. I'm not going to ask you to ever do these. If you wake up in the middle of the night and say, but how do we know that there are always 180 degrees in a triangle? Look, here's one that tells you about it. If you wake up and go, but transversals, how do we know that all those large and small angles are always going to be the same? There it is. There's the proof. All right? So you don't have to know how to do it, but I'm very happy that it's in your brain. Lesson 30 is now complete. And again, the homework part of it is just the deductive reasoning, which hopefully you get. Yay, done. Goodbye.